What I'm using these sessions for is to sort of not just introduce sort of regression, which we've already seen, but also approaches to doing machine learning, how machine learning is done in practice. In particular, we've looked at optimization and objective functions. So what I'm going to do today, though, is map those objective functions back onto probability. Now, an objective function doesn't have to be a probability. It's a good way of developing objective functions for machine learning. So you can have objective functions that are non-probabilistic. But it turns out the one for movie recommendations has a very good probabilistic interpretation. So what you did in the lab last time is we looked at movie recommendation and matrix factorization, and you minimized the sum of squares objectives by steepest descent and stochastic gradient descent. Actually, stochastic gradient descent is the sort of a good way of doing that because of the data is very sparse. You didn't have recommendations for every individual. But this time we're going to explore a more classical least squares and fixed point updates. So last time we looked at gradient descent and stochastic gradient descent as ways of maximizing the likelihood or minimizing the error function. But this time what we're going to do is we're going to look at fixed point equations. So these are update equations that take us straight to the solution. So we've already talked about regression. I've had these examples up before. So predict a real value y given some inputs x. So in the book, you'll see that they use this data here. This is from the 2012 Olympics. People say Usain Bolt's a slow starter. I can't see any particular difference. I think, is that Bolt? I think that's Bolt. There from 2012 in the final. And they do regression on those data. So those data look like this. I've just loaded them up. You can load them up from pods. They're in pods already. So you can see it saying data as pods.datasets, Olympic 100 meters men. And then we're just plotting the x, which is the year. And so I think the data is only going to 2008 because it's the Rogers and Girolami data. And then you're seeing from 1896, the first Olympics, and you see people get faster. So 12 seconds. I'm sure this is not true, but I always think, everyone said, oh, there's a boy in our school that can do 12 seconds for 100 meters. No, I don't think. I think maybe 12 and a half. But 12 seconds dead, 1896, going down to whatever, 9 point something extraordinary. That's used recently. But actually, when I was giving these lectures in Uganda, I was playing with this data, and I thought, actually, Ugandans aren't so interested maybe in the sprinting, but they are very interested in this guy. So this is, anyone here lived or been to Uganda? Does anyone know who this is? Well, anyone know who this is? It's not going to work on the video, putting my hand over the... It's a guy called Stephen Kiprotich. So he's a Ugandan, but he comes from the area close to the Kenyan border. And he won the 2012 Olympic marathon. And he's a massive hero. Uganda has two Olympic gold medal winners. One from like 1972, Akibua in the 400 meters hurdles. And then this guy, Stephen Kiprotich. And it was unexpected. He beat all the Kenyans. You know, that's like the best if you beat your rival country. So they're very thrilled. So when I gave the lecture in Uganda, I started using marathon data. And actually, it's very interesting data. Because, again, we've got all the data since 1896, but they didn't have a standardized distance on those early ones. It was just like anything over 40 kilometers. In fact, I think it was 40 kilometers. And then in 1904, in St. Louis, the marathon was really badly organized. They got lost, and there was a lot of dust on the road, and basically the time was really slow. So these are paces in minutes per kilometer. So actually, I've run a marathon. I run it about here. Something like that, so I wouldn't have won the St. Louis one. But that's pretty slow, right? Because they got lost and only like 6 people finished. So that's like an outlier, yeah? And then you can see what's going on is it's sort of going down. I mean, this is just extraordinary. This is like, who here's ever done the park run? Does anyone know what the park run is? 5K? It's a 5K run around, yes, some people nodding, around Endcliffe Park. So these speeds would win our park run. Like by quite a long way. And people do that for a marathon. It's just amazing. That would be a 15-minute 5K. And they just go and go and go. There was a film called Run, Fat Boy, Run, where in the film the premise was they started off sprinting and they caught up with the elite runners. No, you sprinting, after about, you'd stay with them for like 200 meters, and then they'd leave you for dead. That's super fast. It's just extraordinary when you think how fast they run and how long they do it. I think it's when you actually, if you tried it, I think it's more incredible even than Bolt, who is also incredible. So what we want to do, I don't know, I've got some messed up thing here. Let's see if we can get that to reformat. Yep. Is go back to what we're trying to do is we're trying to take this data, this is data we've got, and make a prediction about what's going to happen into the future. There we've got some data, and we want to know what, say, in 2016 in Rio, what the marathon time's going to be. So we make a prediction, and we do that from a model. And what we've been looking at is a linear model of this form. So now, actually, these linear models have some sort of interpretation. So yi is now the winning pace, and minutes per kilometer. X is the year of the Olympics. M is a gradient, so it's actually a rate of improvement, of human improvement over time. And C is the winning time at year 0. So that's like how fast, it's not Jesus, because he was sort of born then, so he couldn't have run the marathon. But it's like Jesus' mum and dad, Joseph and Mary, that's how fast they would have run the marathon, in theory. That's what the model says. I mean, but you can already see that's ridiculous, right? Because when we fit a linear model, it's not going to happen, is it? I mean, but that's it's interesting that linear models are very widely used in statistics, and these rates are interpreted. I mean, and I think there's very good reasons to it. Sometimes you use an overly simple model because you just want to answer the question. You may not be able to see, are humans getting faster over time? And this will answer that question. It won't give you a rate that's accurate predicting into the future, but it will say that humans are getting faster over time. So sometimes you do an overly simple model. I mean, but clearly this isn't going to be a great idea when we fit it. But of course we had this problem with overdetermined systems that I talked about last week. If we've got these data, then how do we fit, we've been looking at objective functions. But the way I introduced the overdetermined systems is by this person here. Now who's this person? We've already done this before. Laplace, thank you. That's the main thing you have to learn from the course. That is Laplace. He's super important, just extraordinary. His fingerprints are all over all mathematics everywhere. So what did Laplace do? Well, Laplace's idea was that we turn this overdetermined system into an underdetermined one by adding a new parameter or variable. Now, the difference between a parameter and a variable, I suppose that would probably be considered a variable by most people. So an unobserved latent variable, epsilon. But if it's unobserved, we have to do something with it. And Laplace's idea was that you put a probability distribution over it. So you say that that unobserved latent variable, which represents the difference between what we observe and what our model says and what the real world produces. So the real world produces something different from our model. So our model is saying this, and then this is the corruption that comes from the mismatch between our model and the real world. And the way we deal with that corruption is as a probability distribution. Damn, come on. So here's the probability that we're going to use. We're going to use the Gaussian density. Now, the reason it's called the Gaussian density, as you'll see in today's lab, is because while Laplace came up with this idea, the first person to suggest using this distribution in that role was Gauss. And although Gauss, when he does it, he credits Laplace for inventing the distribution. So Laplace invented the distribution, according to Gauss. Actually, de Moivre also developed the same distribution in a different context. But Gauss knew about this distribution because of Laplace, and the approach to modeling data was Laplace's as well. So it's kind of funny it ends up with Gauss's name on it. And then we typically denote Gaussians in this form. So what this says is, look, the probability distribution is over y with a mean mu and a variance sigma squared. So mu is the mean, sometimes called a location parameter, because it's subtracting off the data. It moves the distribution around. So whenever you see a probability distribution in a functional form with probability density, I should say, with something subtract, that's known as a location parameter. This is a scale parameter, sigma. Well, it's an inverse scale because it's dividing into y. So you could actually bring it up here under the scale, under the location. So it's a scale parameter, but it's known as the variance. And it looks like this in, gee, it's really messing up there. In practice. So here I've drawn it as a model of heights, potentially, of student heights in meters. So I've said that the average height of a student is 1.7 meters, and the standard deviation is the square root of this, whatever that is. This is roughly accurate. I looked up some data and just fitted that. So the mean is in the center there, and the variance dictates how wide it is, but we tend to write that down in terms of the standard deviation, which I probably should have put on this plot, which will give us the width of this distribution, this density. So what we're sort of saying is, just as what we're saying in this model is that, okay, so we expect heights to come out as 1.7 with some corruption either side. Now what we're going to say for the Olympic data is we expect the pace to be given by the line, that linear straight line, and we expect that to give us the mean, and then there'll be some variation either side. So we actually sample epsilon from a distribution with zero mean. So that's the form again, but what we're going to do is, instead of having the location parameter just as a standard thing, we make the location parameter dependent on our prediction function, on our mx plus c. So instead we replace mu in here with mx plus c, or actually it'll appear as minus mx minus c. Because then what we're saying is that our probability distribution is no longer dependent on mu, it's dependent on x, the year in which these occurred. And that's what we want. We want to make a prediction over y given some value for x. So just why do we use Gaussians? Well, just a brief sort of review of some important properties of Gaussians. You should have studied these before. The reason I want to mention them again is because I want to highlight that they're very special. So this is an odd property. The sum of Gaussian variables is also Gaussian. It's a very strange property. Now you probably think it's a normal property because it's a property of the normal distribution. Because you're introduced this distribution quite early on and you're shown this property and you don't think anything about it. You just think, oh, okay, well, if you add Gaussian distributed variables to each other, they stay Gaussian. That's very, very unusual. In fact, most other samples from other distributions tend to become Gaussian as you add them together. So if I take even dice, discrete variables, and I add dice rolls together, and I look at the sum of 100 dice rolls, that will look like a Gaussian. So it doesn't look like a 1 to 6 uniform distribution anymore. It looks like a Gaussian. So any distribution you start adding together, as long as it's got a finite mean and variance, the central limiter theorem applies and the thing starts to look Gaussian. Now this property turns out to be very important for processing Gaussian random variables, because what it means is, as soon as you see an outcome of some set of events where you've added 5 or 6 events together, unless the underlying distribution is Gaussian, or there's a couple of exceptions, Poisson and gamma under certain conditions for the gamma, then the result of adding those 5 together is no longer in the class of probability distributions you first looked at. And that's a massive headache. Basically, very often, you can't write down the class of probability distributions you have, of densities. So this property is very unusual, and it's one reason the Gaussian is very widely used. The sum of any sort of set of variables sampled from the Gaussian is given by a Gaussian density. It's distributed as a Gaussian density with the mean as the sum of the means and the variance the sum of the variances. So that turns out to be really important later at the end of the course when we do Gaussian processes. That's sort of why Gaussian processes work. So the other one is scaling a Gaussian leads to also a Gaussian density too. So if I have a Gaussian sample with mean and variance like this, then the scaled version of that Gaussian, if I sort of then say, instead of looking at y, I'm just going to look at y times w, then I find its sample is distributed like this. As you can see why sigma squared is like a scale parameter. It just increases the variance. Yeah? So the new variance, the new mean is w times the old mean, and the new variance is w times the old variance. This is not an unusual property. This happens in a lot of densities, that you get the same form of distribution. It's not unusual like the previous property. This is kind of, it's just a rescaling. So that's very natural for any density. In fact, all densities will stay in the same family. So the Laplace's idea is effectively to define what I think of as a probabilistic or a stochastic process. So if you've done engineering, you'll know what a deterministic process is. It's some sort of set of deterministic operations you apply. A stochastic process is one where the result is stochastic. It's stochastic because of this formula here, that it says that the result we observe, y, is given by the prediction function, which here I've denoted f of x. So f of x is our mx plus c in this case, but it could be any f of x, and that's our prediction function. Yeah, f of x. So I'll always use f for the prediction function. The data minus our prediction function squared divided by the standard deviation squared. That's the probability distribution of y given x. So in some sense, this is a noisy function. It's like take a function and then add noise to it. So sometimes it's known as a stochastic process. I mean, it's a very simple one, actually. It's a very, very simple stochastic process, one that you probably wouldn't see talked about much as a stochastic process, but is a stochastic process because you've added noise to a deterministic process, f of x. So that was Laplace's idea, that the way you deal with this is that so whatever your prediction is, his predictions weren't linear because he was interested in planet orbits, this sort of thing. So he was actually making predictions about, I mean, very complex, because like the Earth spins and the planet does this, and you get these little twists. So they're quite complex models. That was his prediction that comes from Kepler's laws, also derived from Newton's laws. And then he was saying, but what I observe is corrupted. Of course, he didn't use this formula, though. It was Gauss that sort of suggested this. And in your lecture slides, you have the actual bit where in the book where Gauss sort of proposes that. So, for example, we could imagine predicting height as a function of weight. So if weight was our input x and then height was our output y, then we've got a formula like this. So what we observe is not actually the height and weight itself. It's some corrupted version. So we sort of say, I predict that I can get your height by taking your weight as input and then corrupting it by some noise. So y is height and x is weight. So that could be a prediction we make. Okay, so any questions at that point? Because I'm going to move on to the likelihood now. So I'll just pause there, see if you get what we're saying. What we're saying is that what we observe is equal to some prediction function plus a corrupting noise. And when we make that noise epsilon Gaussian, what we're effectively doing is just changing the mean of this system. So this gives us this data point likelihood, which for our case, where we've said f of x is mx plus c, we get a mx minus c in here. Okay? So questions there? Yeah? This is like really fundamental because what we're doing is we're composing a model. This is the reason I teach it in this way rather than just go, oh, here's least squares, right? We did that last week, actually. But the reason I teach it in this way is because this approach to modeling is extendable. It's extendable to lots of different ways, classification, unsupervised learning. What you're doing is you're writing down a probability distribution, which you think is it's called a probability distribution you think is a description, a probabilistic description of how your data is generated. Once you've got that, how you then fit the probability distribution is what we're going to do next, which is known as maximum likelihood. So is everyone clear on where we are now? I'll just pause and shut up for a moment. Questions? No? Okay.
The epsilon.
Pardon?
What, there was an epsilon in there.
Yes, okay. Yep. What happened to the epsilon? Yeah, in effect, I've sort of effectively skipped a step. So this f of x is mx plus c, and we're adding noise to the mx plus c. So in some sense, I just marginalize out the epsilon. So by adding, what I'm doing, what this equation is saying is that, okay, if we ignore that, y would be equal to epsilon, and then y would just be distributed like this. But if I put that back in, it shifts the mean. So when we look at the next, this is the mean, the f of x, which is mx plus c. So the function becomes the mean, yeah. So epsilon sort of disappeared. You can still recover it. Epsilon can be found by looking at y and subtract. It's known as the residual, actually, in statistics. If you can look at the residual, which would be the value of epsilon, or an estimate of the value of epsilon. So that would be, the epsilon would be the difference between your prediction and the actual truth. It's known as the residual. Other questions? That was a good question. Good clarification. Some of you are thinking, oh, yeah. Okay. Okay. Now, that's one data point. So actually, this is just a prediction for one data point given one input, what it will be. But what we need to do is we need to make a prediction for the entire data set. So what we're going to do is have to make a further assumption. What we really want is not a probability distribution of, and this is actually, in all my research, this is the way I look at things. I don't really want a probability distribution of yi given xi. What I really want is a probability distribution of the entire training set, y, the vector y, given the entire vector x. And then often we use theta for parameters. So here the parameters are m, c, and sigma. So that's what I really want, a joint probability over everything. And in fact, at the end of the course, we'll look at Gaussian processes, and that turns out to be what I specify, a joint distribution with correlations over everything. But what we're going to do here is we're going to use a classic assumption. I think that this assumption is very uninteresting. I mean, it's interesting, it's widely used. I shouldn't say it's uninteresting. It's so widely used, people feel it's the only way of modeling, and that's very, very damaging. But it's the main way, and it's the right thing to introduce first. That we're going to assume independence of, well, it's actually what Gauss would have assumed as well. We're going to assume independence of epsilon I. So epsilon I here, we assume it's independent across every sample. So the question is, like, every time you take a measurement, is the error of this measurement correlated with the error of the previous measurement? Yeah? So what you're saying is no, there's no dependence. Remember, we reviewed probability in week 1, and independence would mean that the distribution over the y's, or over the epsilons, let's say. So this is a probability distribution over all the epsilons jointly. And what we say is that there's actually a product of I equals 1 to n of each of these things independently. That's an independence assumption. So that means that the marginal distribution is the same as so marginalizing these things out is trivial. If you want to look at the marginal, it's just that. So when we do that, that maps through to this for y. So what we assume is that the distribution over all y and x is given by this product over the individual y's and x's. This is called an IID assumption. So it's independent and identically distributed. So what it's saying is that every time I observe a data point, that point is sampled independently, but it's also identically distributed to the previous one. So I keep this distribution. I don't change this distribution. The parameters are staying the same, you see? So you end up with n of these things. Now, that's called the data, that's the likelihood. That's the data set likelihood. And it's super common to see it treated as independent. So looking at that for the Gaussian model, what we're saying is that the probability over y given x is a product over all these little Gaussians. Now, the nice thing here, and this is why exponentials are really fun, they are fun, I assure you, is when you pull this product in here, then what you get here is, instead of a square root, you get this is raised to the power of n over 2. And then because this is an exponential, the product of two exponentials is the sum of their exponents. So if I have e to exponential of a, exponential of b, or a exponentiated, b exponentiated, that's equal to a plus b exponentiated. Yeah? And this is just applying that trick multiple times to give us this sum inside the exponential. So that's the form of the likelihood. This is now we've gone from a prediction function. The prediction function is still embedded in our model here as a negative. This would be f of x, this bit here. But this is our likelihood function. Now the likelihood function forms the basis of our objective function for probabilistic modeling. So what we want to do is we want to maximize the likelihood function. So what we want to do is make the data as probable as possible given the parameters. And this is what this function is saying. This is saying, so you can look at this function and you see the probability of y, which is the data. X is kind of a bit weird. It's conditioned on x. So it's sort of, I think it is data, but I don't think of it so much as data. You're trying to, this function, the likelihood function, if you're trying to make it, the reason it's a function is because it's a function as a result of m and c. It's a distribution as well, a density over y, and it's a function of m and c. So when we come to optimize it, we're considering the fact, we call it the likelihood function. We're maximizing the likelihood function because we're going to maximize it with respect to these parameters. We're trying to find a slope and an offset of this function such that the probability of y is maximized. Yeah? So the probability of the data we observed is at its highest. And this goes all the way back to Laplace and before. It's felt to them the most natural thing to do. It was also studied extensively in statistics by Fisher and others as an approach where the term maximum likelihood comes from. So it looks like a nasty function to maximize, doesn't it? Because it's got a sort of exponential in it and stuff like that. So what we don't do, though, is we don't maximize that directly. What we maximize always, you'll always see this, is the log likelihood. You can do this because log is a monotonic function. I thought, so because log is a monotonic, the maximum of this function is some value for m and c. But if I take the log of this function, the maximum for that function is still the same value of m and c. And the reason we take the log is because it gives us this nice simple form. So because log's a monotonic function. I wonder if is that better if I try and take out the let's get that too. Why is it going around the line? That's what I want to know. Some blah 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 blah. Oh, okay. Well, I think it's just typesetting it around the line. Let's try and get it a little bit smaller. Boom. Oh. No. Okay, I know. No. So I wanted them both on the same line. Actually, probably it's not a bad point to split. So this is the log of that function. So there's two parts. One is what was inside the exponential, the exponent, which is now this sum, because it was the product, the sum came inside, and so we just have this sum from inside the exponent. So negative that. This bit is from the first part. So let's just go back and look at how that comes about. So the first part is the log of this object here. So that's log of a over b would be log of a minus log of b. Agreed? But log of 1 is 0. So we just get a minus log of b. Now b itself here is b to the power of a. So I'm overusing notation, but you see what I mean. So down here we've got a log of b to the power of a, but log of that is a times log b. Yeah? So this is an a times log b, where this inside the bracket is log b. And then what I've done, but it's got a negative in front because of this, what I've done then is saying a times, so this is now b times c inside here, a times log b plus log c, because log of bc is log of b plus log of c. So what you'll see is you've got an n over 2, sorry, a minus n over 2 log 2 pi minus n over 2 log sigma squared. You could also bring the 2 through, but we don't bring the 2 through. You could put this 2 on top here, right, because it's sigma squared if you wanted to, but traditionally we don't, because we tend to think of the parameter, well, we're going to think of the parameter as the variance. You can parameterize in different ways. So that's where those terms are coming out. And then log is just these are natural logs. We're always going to be using natural logs. So the exponential here is just cancelled out. That just disappears. So now you should start seeing where we're going. This is the sum of squares error scaled by sigma squared. Yeah? So this is the thing we were looking at last time, only with an additional scaling sigma squared on it. And this term here doesn't have the data or m or c in. So the only terms of this function, if we want to maximize this log likelihood, are m and c. Sorry, any terms where m and c appears are this sum of squares error. But there's this additional thing, sigma squared, which was this noise variance, which wasn't appearing before. Okay, so now there's a property in statistics for these IID models that was studied a bit and people like, that talks about the consistency of maximum likelihood. We're not going to really go into too much of the details of it, but what it says is that if the data was generally generated according to the probability we specified, yeah, the correct parameters will be discovered in the limit as the number of data goes to infinity. Okay, so it's and this is proven through something called a sample-based approximation, the law of large numbers, to the KL divergence between two distributions. I used to have that in, but I don't know. I think it's we're doing more lab work, so I've taken it out. That's actually if you get more advanced, this is a nice thing to look at. Does this matter? Well, I really want to say no, it doesn't matter to a large extent, because none of these things are ever true. I mean, this is nice in the background to know that if it was always true, that you would recover the true probability distribution. But number one, your data will not be generated according to the probability you specify. Not unless you generated the data yourself from that probability distribution just earlier. That just won't happen. And even if it did happen, you never get given infinite data. Or if you do, then that causes you to do infinite compute. So this is some sort of sanity check that this thing does work as the limit of data goes high, but actually we're much more interested in the behavior of the models as you converge towards it. So this is a good justification of maximum likelihood. It's called consistency, that maximum likelihood will recover the right result in the limit of infinite data. But what we'll see when we look at generalization and basis functions, that it will give you some nasty characteristics when you have too little data. So it'll overfit. And even if you've got the right model, even if this is true, if you don't have enough data, you will overfit. I don't like that term so much, but it is applicable here. And if you don't have the right model, if your model is too simple, you underfit. And it turns out there's always a trade-off. You're always doing one or the other, overfitting or underfitting. So that's called the bias variance dilemma. So the error functions we looked at last time is that the probabilistic interpretation for the error function is that it's the negative log likelihood. So the objective function you use for probability is the negative log likelihood. So why negative? Because objective functions, this is just a standard, right? It's nothing, it's just in optimization, they're not optimists in that they prefer to minimize things rather than maximize things. So it's standard in optimization theory. If you read all the texts, they'll always talk about minimization, like the real texts. So we want a maximum likelihood, but because optimization theory is really about minimization, we just say we'll minimize the negative log likelihood. That gives us a maximum likelihood. And that's just a convention. It's just they happen to set that up, just like driving on the left or driving on the right, or the way we do our design matrix. So we'll stick to that. So we always think in terms of optimization about minimizing, even though we're actually trying to maximize a probability. We're going to look at the negative log likelihood. So the maximum likelihood is equivalent to maximizing the log likelihood is equivalent to maximizing the likelihood because log is monotonic, and minimizing the error function is equivalent to maximum likelihood because of the negative log likelihood, because minimizing an error function is equivalent to maximizing the log likelihood. Oh. So if we look at it from those terms, we see that the negative log likelihood we've been talking about has this form. It's n over 2 log sigma squared plus 1 over 2 sigma squared times that. And learning proceeds by minimizing this error function. Now, that's what you've been doing. That's what you did last time. If you did the gradients of this, all you would find is they're just scaled by sigma squared. And if you set sigma squared to 1, you would have exactly the same thing because this term would also disappear, right? So in effect, what you were minimizing last time was this with sigma squared set to 1. Now there's an additional parameter. But what we're not going to do is look at the gradient descent. What we'll do instead is look at, so that's the sum of squares connection. Oh, missing one of those there. That's the sum of squares connection. So this is what you did sort of last time. But there's, just as before, there's two functions involved. And this is going to be, this is pretty much every machine learning algorithm will have some setup like this. There's a prediction function and then there's an objective function. So this is the thing you're minimizing, but this is the thing you use to predict. The error function depends on the parameters through the prediction function. So this, I haven't denoted it here, but this is actually a function of those parameters as well. Okay? Okay, so we looked at that last time. But what we're going to do this time is something a little bit different to what we did last time. So learning is optimization. I mean, machine learning is always some form of optimization, or arguably I would say it's also inference. But the way we're looking at it now, what I describe the separation between optimization and inference, sorry, learning and inference as optimization and probabilistic modeling, which we see later. But so I think of learning just as optimization. So minimization of this error function. Now what you did last time was you computed the gradient with respect to m and the gradient with respect to c, and they had this form. But what we're going to do this time is look for a fixed point equation. So the minima of these functions will exist it's a quadratic form actually as a function of m. It's quadratic. So you've got e of m. It's somewhere like this. And what you're trying to do is find the location of this minima. Sometimes we call that m star. The value of this thing that minimizes this function. But what you can do is just look for the position where the gradient of the function is equal to 0. So the gradient at a minima, stationary point, is equal to 0. Because this function happens to be convex, this is a convex function, meaning its curvature is always positive. It means that just if you find the one point where the gradient's 0, you'll be at a minima. And that's what this equation is saying. Look, so we're now setting this gradient equation to 0. This is called a fixed point equation. Now we'll reorganize this gradient equation such that, and you're going to have to do that in your own time. So go through this in your own time. The way I've done this is in a two-step thing. First of all, I've multiplied out that bracket, yeah? And once I multiplied out that bracket, I've collected the terms in m, which involves bringing that sum over xi squared, brought them over the other side, and then divided the xi squared through here. So if you look at this, this is just a recollection of this and this divided by the 2xi squared. Yeah, so it's simple algebraic manipulation. That gives me a fixed point equation for m, or I might say m star. That will take me directly there. So you spent all that time last week going digga, digga, digga. You were going dig, 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 dig. And this week I'm showing you, you can just go bang, straight to there. So you're thinking, why did I make you do that? Well, because sometimes that's a very good idea. And actually it turns out, as you'll see this week, this can be a very bad idea, doing it this way. Similar for C, same job. So we just get, so we've got that for M, and then we have the same for C. Okay? So there's a C star here, and again, the formula is quadratic. There's the gradient. It's a slightly different result. There's no, the formula for C is obvious in retrospect. Look, it's saying, take off all the bit that mx explains and divide it by m. It's like a formula for a mean. If m was 0, it would just be the formula for the mean. So, but it's not 0 typically, so it's got that sort of form. So that's great. So we've got formula for m and formula for c. Who can see a problem with this? One formula for M and one formula for C. What does the formula for C depend on? M. So how do we know the value of M to put in for the formula of C? Use the previous one. That's correct. So how do we get then, but then what do we do next? Is that going to be sufficient? So what actually happens is, for some cases, and it very much happens in linear regression, is if you use formulae like this, I need the board rubber, is that you get a problem. Because I've drawn two contours, slices through the error surface. But the way we should think about this error surface is as a two-dimensional one, and you'll plot this in the lab. And you'll see it's also in the PDF version of these notes. If you have correlations, it's when you have correlations that you get problems. So you've got a quadratic error surface. So this is the minima. This is like M opt, comma, C opt. And then this is, in this axis, I can't remember which way around I've got it. I think it's M and C. If you start here with a value of M and C, well, you just have to start for a value of M, for example. So if you start this value of, if you fix the value of M and optimize according to C, the plot I was showing before is the slice through this part of the objective. It gives me a quadratic. And optimizing along this will take me to the middle. But now I have to optimize along this direction here, which will take me to the middle. And what you find is you do this. And you'll find that optimization is extremely slow. What you were doing last time was actually to start here and just take gradient steps. Yeah, like that. Or then stochastic gradient, you were going dick, 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 sort of like down like that. Yeah? Here, what you're going to do is your first step's great. It takes you somewhere in the middle. But once you're in the middle, you're sort of like at the bottom of this valley where you're only allowed to go left and right. So you end up going duck, duck. Oh, that's the minima. Duck, duck. And that's how you get down the valley. And it's really, really slow. You'll see that. And this is called coordinate descent. So it's called coordinate descent because you're constrained to minimize. And it's quite a common approach. It appears in many different regimes. The sort of classes of optimization you're broadly seeing are being covering the basis here. So because you only move in the direction of the coordinates being the axis here. So you're not allowed to do, if you were allowed to do that move, if that was your coordinate, so for example, if you were really lucky, and this doesn't really happen with real data, then if you started here, then you would sort of minimize in this direction, you would end up here, and then you would go here, and then you would do it in 2 steps. 2 steps, bang. But that isn't what happened. What tends to happen is you get this strong correlation between M and C. The reason being, the right value for C is heavily related to the right value for M. And you tend to get this, and it's very, very slow. And you'll see an example of that in the lab. So there's also, you can also, in your own time, you can work out what the fixed point update is for sigma squared. Sigma squared is great because neither of these guys depend on it. So you don't have to include sigma squared in your iteration. You have to optimize between these two. And when you're satisfied you've got the right values for these two, then you can compute your value for sigma squared in one shot. Okay? So sigma squared is great. But M and C aren't so good. And you have to do this sort of nasty iteration. So there'll be a worked example in the lab where you do that. Now in the last 5 minutes I'm going to sort of, that's kind of mainly what we'll talk about in terms of optimization methods. So I've showed you gradient descent, stochastic gradient descent, and coordinate gradient descent, stochastic gradient descent, and coordinate descent. These are some important extensions which we're not really going to cover in the course, but would be often how you do some things in practice. Second order methods that consider the curvature of the surface you're working in. Conjugate gradients which try and find clever directions. So conjugate gradients actually try and find these sort of axes. They try and move along these axes. They sort of learn what those axes are as they go along in effect. And they only take orthogonal steps. Conjugate gradient and quasi-Newton. These two are sort of related. And Newton steps just take the full curvature in. And heuristics such as momentum for stochastic gradient descent is really powerful. That's widely used. So we're not going to talk about those much because we're sort of pushing more onto the modeling side. The other thing we're not going to talk about much is local versus global solutions. So when you're minimizing an objective function, you always get this problem that if you've got an objective function which is multimodal like that, you might want to be here, but you often end up here. And finding the global solution is really difficult, pretty much impossible in a large parameter space. So you often normally, if you have this situation, you're often normally in a local solution only. I think all the models we'll look at, you don't have this situation. You get this situation with neural networks. Now, neural networks are very interesting. I'm not going to talk about them in a great deal in the course because, to my mind, you shouldn't be allowed to look at neural networks until you've understood everything what I've taught. But once you've understood everything I've taught, it's really easy to understand a neural network properly. Not to understand it, oh, there's a neuron and it's doing this and it's thinking this. No, but to understand it from a modeling perspective. I mean, I could give you a sort of 20-minute lecture on neural networks once you finish this course, and then you would see how they fit into the scheme of things. But if I introduce them straight away, it's too much, I think. So there's some reading there, but the thing that I'm going to then talk about in the lab, I'm just going to give you a quick review of. So there's some reading there, and another objective of today's lab session is to persuade you, by forcing you to do this horrible optimization, that linear algebra is really, really useful. Right? So in today's lab, we're also going to go beyond linear regression in the form we've seen it, and we're going to go to multivariate linear regression. So multivariate linear regression is where the output is now a weighted sum of different x's. So maybe our height depends on our weight, but also depends on aspects of our genome. So people use these linear models on genotyping. So on which particular mutations. So X might be whether or not particular mutations are present. So you start explaining height, not just by your weight, but by aspects of your genotype. In fact, you would perhaps drop the weight and try and explain aspects of your height by your genotype. These are the sort of things people do in heritability analysis. So here you've got sort of P different mutations in your genome that you're using to explain your height. And we want to know how important each one is. Is a particular mutation making you taller or is it making you shorter? That's what the W's would give us. So if we had a population of enough people in all these mutations in the genome, then we could do that. Now, that mass is kind of ugly. It's an inner product, and I prefer the, I don't like the sum sign. I like the sum sign sometimes, but for this case, I prefer to use this notation. And in fact, I prefer to absorb C in by sort of always assuming you have this extra input x0, which is 1. So rather than have this C hanging around, just say, OK, I can just assume that I've got an input x0. Maybe algorithmically I don't do, but mathematically I do that. So this is just the same thing, but written in a vector form. Now, the amazing thing about that is, and I'm going to go through this very quickly, but I'll go through it again in the lab, is we can now use exactly the same formalism. All we're changing is the prediction function. Yeah, so instead of mx plus c, here we've got a prediction function which is w transpose x, the inner product. So this is now all the features combining together to give us the output. The log likelihood is that form, the error function is that form. Now we have to optimize with respect to w. Now notice that what we did before is a special case of this, because the special case is where x is two-dimensional, x1 is our old x, and x0 is just 1. And w1 would be m and w0 is c. Yeah? Going back to this formula here, it's perhaps clearer to see that in the sum form. This is just, before we had mx plus c. Now we're saying sum of w's times all the x's. So if w1 was m and xi1 was the old x, that would be mx. And if xi0 was 1 and w0 was c, then we would get mx plus c. So I'm having to remove c there. OK? So this is a general case. This generalizes the linear regression we did before. But what it needs is, when we expand the brackets, is this form. So the expanding of the brackets is the same as before, but look, because this was before, we could just write m x, this would be like, when we expanded the brackets, this would be the, we would get an mx plus c in here, and this thing would look in quite different to this. I've written it in this particular way. W transpose xi, this is just this squared, right? This is a scalar, and that's a scalar. It doesn't matter which way around I put it. So W transpose xi is a scalar, and I could just put W transpose xi squared to expand those brackets, and that might be a bit more familiar. But the reason I've written it like that is because I can now carry the sums through. So I've got all these sums, but what I can notice is that this sum here comes inside the W, like this. So that's just a rewriting of that. So before we would have had mx plus c squared in this term here, and then that was expanded out. But rather than expanding that out, we've written it in this form. Now notice what's happened. This is an outer product. So this thing is a matrix. Okay? So because this is not an inner product, it's not vector times vector like that. It's oh, am I the right way round for you? Wait, is that vector times, yeah, vector times vector like that. Oh God, it's not that. It's sort of that, which is giving us the outer product. So the elements of this matrix for 1i will be x11, x12, x13, x14, and then down the row the same. It's a symmetric matrix, and then that's summed across all I. So it's a big matrix, actually. And that matrix describes this structure, actually. It's describing this curvature in high dimensions. It tells us what the correlations are in this system. It's the fundamental matrix underlying the error function. It's the quadratic form. See, this is W transpose this matrix times W. This is known as a quadratic form. So that's the fundamental object we're going to need to optimize. And I'll tell you more. I'll show you how we do that with matrix calculus during the lab class. But we have to finish there because there's a lecture after us. So any quick questions? Very quick questions. Let me bring that back up, I suppose. So I'm going to carry on with some of the optimization of that at the beginning of the lab class. But any questions about that at the moment? We can ask more in the lab class. Okay, let's pack up now then, and I'll see you at